Jess is one of the SANS DFIR faculty, and he's been teaching with us for quite some time. 15 years. He's one of our long-standing instructors. Teaches a wide variety of courses, and he brings a lot of experience from a variety of different sectors, big industries supporting finance, insurance, communications industry, healthcare industry, with a lot of different high science type organizations as well. He's got some background with the European Space Agency and NASA as well. Now, Jess is going to be talking to us about a topic that I'm really excited about. He's going to be talking about data science, and I promise that we didn't only select his talk because it has The Force Awakens in the title, although I'm a huge Star Wars fan. It's definitely something that I think is going to be really helpful for us as we just start to see consumption of data, agnostic of it being DFIR, data science becoming its own practice. And fortunately now we have the ability to really focus that down toward the DFIR niche. So without further delay, Jess, thank you so much for joining us. And I know it's fairly late where you are, so I'm glad we can get you on the schedule. We're glad to have you, and really excited for you to share some awesome knowledge with us. Welcome.
Thank you, Phil. Thank you very much. Well, let's get started. Okay, I hope you guys enjoyed this little intro. Phil already presented me, so I'm not going to be going any deeper on that. But I would like to introduce this talk. Basically, this talk is the follow-up to a research I started last year in data science applied to forensics. Okay, in general DFIR. So basically, we started a project recently, which is called DS Forensics. The website is dsforensics.io, and we have a mission, okay, for this project: bring the force of data science and artificial intelligence to all forensicators. Why? Because I'm pretty sure data science, specifically AI, is going to be changing the world, and I hope during this presentation I can show you guys a little bit of how this can be useful for us. The idea is not that you become an expert in DS and AI, but the idea is to actually be able to make it easy to use. And I hope this project will help in that endeavor. Basically, we are putting together a number of resources. It stands out the DS Forensics Python library that you will be seeing during this presentation, which basically automates and makes easy many of the things that you guys in terms of analysis on your DFIR work. And also we're going to be putting together blog, news, videos, cheat sheets, a lot of stuff to get you off the ground and in a very simple way, okay? As you will see during the presentation, lots of things that you normally have a hard time to do are very easy to do with this new technique and new environment. I'm a SANS instructor, you know, I cannot help it. And basically, I always live to the SANS promise, okay? That you can use whatever you learned today as soon as you go back to your office. So basically, I've developed this presentation in 3 phases. It's going to be very intense, by the way. There's going to be a lot of content. The first phase is going to be Padawan level, which means easy, let's say, just getting you off the ground in terms of data science basics and the environment and some simple things, but always applied to DFIR, okay? So we're gonna be starting with something simple that most of you know, which is file system timelines, okay? Then we will jump to Jedi level. That's gonna be a little more difficult in terms of using other tools like Volatility, Kansa, Plaso, and see how we can use these new techniques to analyze the data in an easy and at scale format. And the last part of the presentation, which I call Jedi Master level, is going to be getting a little more complicated, which is going to be trying to see ways of more advanced intrusion visualization and machine learning applied to DFIR. See what we can do with that, okay? So for those Star Wars fans in the audience, you may remember that episode 8, The Last Jedi, was a little bit tricky because all of a sudden you have Rose, Finn, and going to the Supremacy Starship in order to try to deactivate a supposed command and control, okay, tracking device which is tracking cyberspace or hyperspace jumps of the rebel fleet. Okay, unfortunately, if you've seen the movie, they fail. Okay, and what happens? Of course, the incident response team, which is us, needs to take over and solve the problem. Okay, so what is our case study in this case? The hyperjack case. We have to find basically the beacon that is beaconing to this Supremacy Starship and disable it. And we don't have a lot of time, as you were seeing, because the fuel is depleting, the shields are depleting, and we need to jump soon. Okay, this is taking place in year 2012, 2211. Okay, just for a reference. And basically, this is our network. Okay, we have 200 space shifts. We are going to be having to do a threat hunting process on those 200 space shifts. I'm just going to be giving you a side note that the data, we've been using multiple sources of data for the presentation in order to enlighten the concepts, but we actually are using real world data from 200 systems, okay, with which we've been doing hunting and doing this process as well, okay? So this is our Starship fleet, okay, with, as you can see, it's funny because we're still using IP version 4 so many years later, but it just works, okay? So this is what we're going to be doing. In order to do that, as I was mentioning, we are going to be using data science, okay? And data science is going to be very interesting and relatively easy to use. The only thing you need is to have a Jupyter environment. You will need to install an Anaconda package, which is very easy to download and install. And then you will have a Jupyter server running, which is basically a browser like the one you see here, which will allow you to run commands and post comments and run a console and many other things. On top of that, you're going to be analyzing the data you produce with your forensic tools, such as Volatility, Kansa, Plaso, and many others, okay? And on top of that, in the red box, you have our data science forensic library, which will be helping us in the topic. So let's start with Pandas. Whenever you see PD in the slides, FSTL equals PD, that means Panda. And this means that reading a CSV in Panda is as simple as that. PD reads CSV and provide the CSV file name. As you can see, the output of that operation is going to be something that we call a data frame. I'm going to be introducing that in a couple of seconds. And it has a number of columns, which is our date, size, type, etc. You already are familiar most probably with file system timelines and those columns. Note that the date column is actually of object type, and in reality should be of date type type, okay? So what we can do, what we need to do after reading the CSV is actually adjusting some columns, like making the date column of date time and dropping, for instance, in Windows some columns which are not really useful for us, like mode, UID, GID. That's super easy to do, as you can see, with the data frame, with the drop function. Everything in data science is so easy, so intuitive, okay? And it can get very sophisticated. On top of that, what we've done in order to facilitate even more those processes, we've created in the data science forensics Python library a number of functions which are going to be taking care of the specifics of our analysis, like the small details of dropping those columns if you're in Windows, or just doing that date type conversion as I was saying. So if you have multiple different tools, like a file system timeline, EVTX, or Plaso, we've created functions which are read FSTL, read EVTX, read Plaso, okay? so it cannot get any easier. This is basically the Pandas data frame. The Pandas data frame is something very intuitive. It's just a two-dimensional array, a matrix, okay? The very small detail about a data frame is that it contains tags. You can see on the top the column tags, date, size, type, etc., and on the lines the 9 numbers. This is going to be instrumental in order to have flexibility to managing the data, because those are not only tags. Those tags are associated with the data itself. So whenever you do something to the data, those tags are going to be staying with the data forever. So that's going to be super useful to do your analysis. A subset, another object that we use in Pandas is the series. You can see as each of these columns of the data frame will be a series. Okay, it's the equivalent of list, but once again with these tags that are very flexible and very easy to use. So let's start with the analysis of the FSTL. First off, a very fast quick win. Any field that you have, which is an integer or a numeric value, you can plot it instantly. So I'm plotting the FSTL field, the size field, and then as you can see here, I can see immediately that there is a file which stands out because it's more than 3 gigabytes in size. Okay, that's pretty cool. And if I do a sort of the data frame by the size column in descending order, you can see that the top entry is a apparently malicious file called dump.bin in the Windows 10 folder. Okay, so let's investigate that a little better. Very quickly, as I told you, there's going to be a number of functions that are going to be helping you from the data science forensics library. There's a function called FSTL size top n, which basically is going to be taking care of small details of the file system timeline, that like those file underscore name annoying entries that sometimes are getting in the way when you're sorting your data. Okay, so let's analyze the Windows 10. As you can see, it's very easy to do any type of search, just doing the string dot contains and then whatever type of search you want to do. Okay, case sensitive and case insensitive is also very easy. And doing just that search in the Windows 10 directory, you will find other two interesting files, b1 and b2.exe. Okie dokie. So now I have some findings. I want to scale up to do analysis of all the executables in the whole 200 starships fleet. Okay, so how can I do that? We've created, of course, you can repeat what I just did, which is not very difficult, right? You could create a small loop in order to do that over and over again. But there is another way. We've created another function which automates that looping, and is called read FSTL's file types. What it will do, it will create the dictionary of data frames in which each data frame is going to be one of the file types that you're specifying. For instance, in this case, we've extracted executables and DLLs. And as such, I will create a data frame called XSFS and DLLs-FS. So two interesting data frames, which, as you can see, are super easy. And then I will have my data frame with all those executables. Okay? If you take a look at this, I can from the executables data frame, I can extract those which contain the Windows System 32 path. I'm going to be doing here a Windows System 32 analysis. Of course, you can do any other type of folder, right? And as you will see, pay attention to the path hash column, which is the last column on the view. Okay, that path hash is nothing else than a hash of the file path in case insensitive way. That's going to be very easy. It's going to be much easier to use that field than using the uppercase and lowercase combination in the path. So we will be using that. If you see the number, the Windows 32exe account for 76,000 rows, which means 76,000 executables. Oh my God, that's quite a few executables to actually deal with. However, one of the very cool things that data science and specifically Pandas has is the group by function. What you can do is group the different entries in the data frame by any combinations of field we want. Okay, if I group them by path hash, I'm going to be generating a a group of 867 individual executables will repeat all over the place. Of course, there are not infinite number of variations of the executables in Windows. It's going to be depending on your patch level and versions of Windows and such. And in total, there are 867. But let's be focusing a little more. If I'm expecting malware, I'm probably going to be finding something which is not installed in all the systems. So I'm going to be restricting that to only 3 Express starships, okay? So how if I take a look at all the binaries in Windows System 32, which appear in less than 3 starships. And you can see the way to get that value here. And guess what? I get only 47, okay? So from 76,000 binaries, I came down to 47, which is completely manageable. If I do the analysis of those 47 binaries, I immediately see that there is one of them which has a timestamp which is very recent. And actually is one of the key Windows 32, one of the key critical processes in Windows, which is LSA ISO. So, that's interesting. We have found till this point, only with file system timeline in a very easy to use, in a very easy way, several interesting findings, okay? Let's jump to the next level. Let's go to some other tools like Volatility, Plaso, Kansa, and some others. We're going to be repeating the same process, okay? If you do a volatility dump, okay, you will have, as you know, TXT files or CSV files, and those TXT or CSV files will need to be read. Is it difficult to read them in Pandas? No, absolutely not. It's super easy. If you have formatted text, you can use the read FWF Pandas function. If you have CSV, you already know you have a CSV function. But wait a minute, volatility gives you only formatted output, right? Well, not really. You have the output correct text option in volatility, which allows you to dump the data in pipe separated format. Okay, that's fantastic, and that's Pandas is super happy to read that. So you can read that with read CSV, specifying of separator of pipe, and there you go. You have your PS list data frame with all the different columns that you already are familiar with about. Okay. Now, what you see here is that in reality, it wouldn't make a lot of difference if you get this PS list from other utilities like PS in Windows or Linux system, or if you get it from any other endpoint solution that actually can get you the process list. The analysis I'm going to be doing is going to be very, very similar. Okay, we have created once again another process, another function in the data science forensics library, which is called read volatility. What does it do? If you have a lot of individual files, okay, out there, which you may have processed with volatility, it's common that you do a lot of processing in your memory image. You can read them all at the same time, okay? So basically, you can have them in a folder, you launch read volatility, and bingo, you have a dictionary of data frames. Individual plugin outputs are going to be in each of the data frames. So a couple of interesting processes that we normally do when we're doing hunting and forensic analysis in the Windows environment, especially from the memory analysis point of view and process analysis point of view, is first off, if there are anomalies of processes that have been started at boot time. Okay, so if you take a look at the fantastic SANS Hunt Evil poster, you will see all these processes that actually appear in which they're the critical process of the system. The poster actually gives you how many times these processes should be running, who is their parent, and if they start at boot time or not, okay? So what we've created is a function that analyzes those critical files and sees if they are actually starting within 30 seconds of boot time or not. And guess what? If you run that analysis with the 30 seconds option that I was mentioning, you will see that there is this LSA ISO that we were mentioning before is actually running in the system, and it's actually was not started at boot time. We can do another similar analysis, I was saying, like the parent process analysis. Doing that manually in any tool is complicated because you don't really have the process name. What you have is the process ID and then the parent process ID, but not the parent process name. So comparing the child with the parent is not very easy. So what we've done is created the volatility processes parent analysis function, which will do that analysis for you. And what do you find? That the LSA ISO process actually has a very interesting parent, hsengine vc.exe. Okay, once again, everything points in the direction that this is a malicious executable running on the system. Let's go for another, for an example, to another artifact, Kansa. Okay, Kansa, many of you know, already know this this framework. It's a PowerShell framework that allows you to search, hand your environment for different type of artifacts, get them in order to analyze them in an easy way. So once again we've created a function to make it easier for you, which is read Kansa, and read Kansa will create once again a dictionary of data frames, and in each data frame you will be able to see each of the things that Kansa actually is parsing. For instance, the services, and then with all the columns in the services you can actually do all your analysis. I'm going to be focusing on auto runs. Okay, so one of the data frames that you've created is an auto runs data frame, and we can do an analysis. You have here a few instructions, which, for instance, eliminates everything that is Microsoft signed binaries. That eliminates a lot of noise, and it will point you in the direction of a few interesting entries. One of the ones that stands out is the run key, the infamous run key. If you analyze that one, which is very easy to do, as you can see from the Pandas point of view, you will see all the contents of that run key. Okay, so once again, once you have the data in such easy to parse format, it's super easy to analyze one column of the other. And by the way, it's not only easy, it's super fast. If you're running a query in hundreds or thousands or hundreds of thousands of lines, I would say even millions, it shouldn't take more than a few seconds, maximum a minute, which is, compared to anything else, is amazing, because Pandas is actually, and the whole data science environment is actually optimized for that. So I'm going to be jumping now to Plaso, which is an amazing tool. I've been loving Plaso since it was born in its origins by Christine in the log timeline. And we've created, many people work with the CSV version of Plaso, which as you know, it can be easily read, and we created the function called read Plaso CSV. But I'm going to be focusing on the JSON output of Plaso. It's very easy to actually generate that JSON output with Plaso, with psort, and actually you will get a format in which the details, the parsed details of the data are inserted. So with read Plaso JSON, you will have individual data frames which contain the parsed artifacts. Okay, let me give you an example. If you look at the prefetch, the Windows prefetch execution data frame, what you will see here is not the general characteristic of Plaso, but it's actually the things like the map files on the round count, the count run, okay, which are the things that belong to the artifact itself. Which is absolutely amazing is that then with just running Plaso on a disk image, which is literally one command with three words, actually will get you all the artifacts in parsed format, okay? And with all the flexibility that the data science environment provides. Going back to our case study, we can analyze the prefetch for the prefetch data frame for the b1.exe and b2, and we actually see that they have actually been executed. And guess what? The LSA ISO has also been executed, and the HS engine as well, this one very profusely. So, looks like we found our beacon, okay? Now, we've been able to kind of solve the case at this point, okay? But let me go to the next level, the Master Jedi level. Can we do something more sophisticated with data science? I'm going to be giving you only two examples very quickly. The first example is going to be analyzing Windows event logs with advanced visualization. What I've done in this case is, first of all, just as you are probably getting familiar, we created a function in the data science forensics library, which is called read EVTX. What will this function do? It will read the event logs, the Windows EVTX, using Willie Valentin's amazing EVTX parser, which we have integrated in the data science forensics library. And it will read the EVTX and generate a set of data frames. As you can see, it generates a data frame for each evidence type, event ID type, and then also a general data frame, which is called all, okay? If you analyze one of the first things you normally want to do when you have your events is identify how many events of each type you have. And it's super easy to do with the value counts function in Pandas. But let's be honest, how many of you really know by heart all the meanings of all the event IDs? Okay, maybe a few, but all of them. So what we've created is yet another easy to use and useful function, which is called event ID stats, which will dump the statistics in a data frame format with the event descriptions. Okay, so what is the ability over other tools? Not only you have the events, but now you can parse everything in the data frame environment, the Pandas environment in Jupyter. Okay, so can you do searches on all your events? Yes, certainly. You can do search a string, any string. We're searching here for a file name and num, and then search that string in your whole event log in a very fast, as I say, very efficient way, and we can get the hits that we need. Another thing that you normally have to do almost every time, and it takes a little bit of effort, and which we have simplified, is take a look at the statistics. For instance, what users have been logging in. I'm focusing now on 4.6.4 events, which tend to be one of the most useful in the Windows event logs, right? So what users are logging in, and from what machines, what IP addresses, what logon types. So we've created this event nonce user stats function, which will basically give you, with just that command, all the statistics information, okay? Allowing you to analyze and identify potentially suspicious entries. But let's get a little deeper. Those 4 fields that I just mentioned, workstation name, IP address, target username, and logon type, are extremely useful. So we've created yet another function, which is very flexible, which is called event nonce user access stats. Okay, what does it do? You provide the data frame with the 4.6.4 events. You provide a first date, a last date, and a periodicity, and it will give you how many times each of that combination actually appears in your data. Okay, so this means that if I'm interested in seeing how many, what combination of user, logon times, workstation IPs happen in a specific hour or day or month or week or year, we can do that this easy, okay? Remember that what you obtain, the Y here, is actually also a data frame. So not only I have the output, but I can also filter in the output for maybe logon type 10 in order to see basically a lateral movement. And to end up with, I'm going to be doing advanced visualization, okay? So what I've done is create a combination of all these 4 parameters and put them all together in the y-axis. And I'm printing that versus time. So if you took a look at the output, well, it's pretty clear that the central line is where the standard user is actually operating. The upper line is probably some type of administrator. And there are another 3 lines which correspond to other users, which are kind of strange, especially if you take a look at the lower bottom user, which is the HS engine user. It contains lots of logins during the last period of time where the intrusion happened from a lot of different locations. So that clearly stands out. As you can see with that visualization, guys, it's super easy to catch strange stuff. The next thing you can do is go one step beyond and put together the same analysis for multiple systems. Okay, we've included here 4 different starships, and each color represents a starship. And on the left, you have actually the users. So as you can see, each user, for the most part, logs in to his own workstation, but there is a user, HS engine, which it actually logins to multiple different workstations. So how difficult it is to see an anomaly with this type of visualization. As you can see, super useful. I'm going to be just going to the last section, which is going to be probably something that is going to be getting you very excited, which is, can we actually apply machine learning to all this process? And I'm not going to be getting, I don't have the time, and I'm not going to be getting very in-depth in the topic, but I'm going to be giving you the big idea. First of all, how do you work with data science in order to create a neural network, okay, in artificial intelligence, machine learning or deep learning? There are a couple of libraries which are extremely useful, Tensorflow and Keras. Keras is a very simple library, which is a wrapper to other machine learning libraries and deep learning libraries like TensorFlow, and it's super easy to use. We're going to be using also another library, which is scikit-learn, which provides generic functions that are also very useful in creating neural networks and artificial intelligence in general. So let me give you an overview of the process, how the machine learning process works. The first thing is data preparation. To be honest, that's where you're going to be spending 80% of your time, okay? Understanding what you want to do, how you're going to be doing, what is the diagnostic data that is useful. Remember, in the previous analysis, I didn't select all the events. I didn't select all the fields. I focus on 4 fields, which are especially interesting, and I focus on 4 6-4 events, which are especially interesting. You need to know your data, and from there, you will be preparing. I'm going to be going on the details now. Then you design your neural network. Then you build it in code. Then you train it, and then you can run your predictions to see if you can find something interesting or not. So how do you prepare your data? Well, there are several steps. First of all, you need to select your features, which are the interesting fields. Remember, in our example, are the workstation name, the IP address, the username, and the logon tag. Okay, I have selected those 4. I could have selected more, and actually machine learning and deep learning algorithms are better the more features you provide to them, as long as they're meaningful, okay? But I want to keep things simple. The second thing what you need to do is normalize your data. Why? Because machine learning algorithms don't like strings. So if I provide this, it's not gonna work. I need to turn this into numbers, okay? So there's gonna be a one-to-one relationship between these strings and those numbers. And how do I do that? With a very easy to use function from scikit-learn, which is called label encoder, okay? That, as simple as that, it will create that mapping. After you do that, machine learning processes require a training and a validation, okay? So it's common to do the splitting of your data into parts, training and validation. Okay, it's very easy to do. There is another function from scikit-learn, which is called train test split, and it will split your data. Normally it's 80-20, okay? 80 for training, 20 for validation. Now you have your data ready. What's going to happen? Now you need to design your neural network. There are lots and lots of different types of neural networks, and there are lots and lots and lots of different types of architectures. I have selected an autoencoder. It's a very simplistic model that is very good at detecting anomalies. Why? Because the way it works is basically creating a model of your data. So basically, I'm going to be putting an example with cats. You're providing cats to the neural network, okay? The neural network, the autoencoder, actually creates a model of the cat, okay? And then it will try to reproduce the cat in the output. This is very useful because this doesn't require you to provide tons of malicious data. On the opposite, you need to provide tons of normal data, okay? Why is this conflicted? Because of course you don't have tons of incidents and tons of malicious data in your environment. So it's good to have a model, and the autoencoder is this model that actually allows you to do that. So what you provide is input, as you provide lots of cats as input. It creates a model of the cat in the middle, and then tries to reproduce the cat. What happens if you provide a dog as an input? Well, a dog is pretty similar to a cat, but it's different, okay? So there's going to be an error of reconstructing the cat on the output. What if I provide an elephant, which is really different? Then the error is going to be tremendous in the output, okay? So what we're going to be doing is basically looking at that error in order to look for anomalies. The first phase, remember, is building your neural network. And guys, it cannot be simpler with Keras. You have 3 layers: input layer, which is the input, the 4 dimensions, note the features at the beginning, 4 features. The input layer is going to be the 4 features. The encoded, which is the representation of your data, which is dimensions, okay? Normally, the autoencoders are good at compressing the data in model, and then the output layer needs to be in the autoencoder the same as the input layer, okay? So it's a shallow neural network. Why? Because it only has one hidden layer, okay? If you have more than 3 hidden layers, that would be called a deep neural network. The phase 4 is going to be training your neural network, okay? So how do you do that? With the fit function in Keras. And as you can see, you look at the output, there is a number of, you can see the loss. At the beginning, it's loss 13, then 10, then 8, then 6, and at the end, it's just 1, okay? And it barely changes. This means that your neural network has learned. It's doing now the right stuff. So we go to the phase 5, and we predict. We provide the data and see what happens when trying to do the reconstruction. And as you can see, if you take a look at the loss, there's a very big spike. In my previous example, that would be the elephant. Okay, it has detected an elephant, which is very obvious. But there are other minor spikes that are also interesting to look at. So if you set a threshold, let's say, an interesting threshold could be 3.8, which doesn't give you a lot of false positives, but give you some of the peaks. This is what you will get. It stands out that HS engine and certain logon types like 9 and 3 are actually detected by this super simple neural network. So let me go one step. At this point, it's like, yoo-hoo, our neural network has been able to detect the intrusion. Not all the intrusion points, but we don't really need that, right? When we are doing threat hunting or incident response, we are not expecting to get all the data points. Just give me 1 or 2, and then I will pull the string from there. So the next thing is, I'm going to be trying to overplot this data on my previous graph and see what happens, okay? See if the neural network actually was able to detect the intrusion. And if you remember the previous intrusion, the lower right corner was where the anomaly was happening. And in here, you can clearly see that there are 4 data points which have been detected. The red data points are the ones that the neural network has detected. And actually, it has been detected automatically with no knowledge on my part in terms of what users, forensic science, etc., forensic knowledge, etc. It was automated. So it's an amazing thing, guys. Imagine what you can do with more sophisticated neural networks models, where you can actually include the timing, which has not been considered here, more features, more events, etc. Artificial intelligence is the future in so many aspects, and it's actually going to be the future of DFIR. So that's why I truly believe in the DSN forensics force, okay? To end up with, guys, this is the end of our case. Hope you enjoyed. And I can only rely you to Yoda's work, okay, words. So please use the form, learn the ways of the force, and use it. I leave here a list of the functions that we've been using in the Python forensic library. We have just uploaded the library and make it public. It's free to use. Download it, use it, look at the code, and that's it, guys. I hope you enjoyed. There's going to be much more coming in the data science, in the dsforensics.io website. Join us, follow us on Twitter, send us your suggestions, send us your comments. We are looking forward to create a community that actually help us promote data science and artificial intelligence in this field. And of course, if you need professional help in order to implement this in your environments, let us know. But let me finish with this, of course, traditional saying, may the DS Forensics Force be with you guys. Hope you enjoyed, and thank you very much. I will be happy to hear any questions afterwards in the channel. Thank you, Bill.
Yep, you got it. Thank you very much, Jess. We do have a couple of questions that are in here in the Q&A. I'm going to leave those up for right now. I'm going to port those into your hallway channel in Discord. We are moving into a break right now, so we're going to come back in just about 5-6 minutes. We'll get a timer up there for you. And during that, you'll also have the link to the evaluations. So if you can jump on in there, we'd appreciate it. Thanks very much, Jess. Fascinating stuff. Our data is not getting smaller, of course, and being able to address it at scale is going to be a very important thing for us to do if we're going to maintain the upper hand in any kind of analysis, especially in the DFIR world. So I'm very excited for the project, and thank you and your folks for bringing that out for everybody. And it's always good to see community resources. Thank you.